So this is a revision video for physics, physics part of CP3 for year 9. So this follows the new GCSE, the 9-1 GCSE for an Excel physics. So this will go through everything you need to know for your end of year exam for year 9. So the first thing we learnt about was vectors and scalars. Not highlighted at all. When it comes to vectors and scalars, remember vectors are quantities that have both size and direction. So direction and magnitude. Magnitude is just a posh word for size. Scalars have just magnitude, in other words, just a size. For an example, force is a vector because it can have a magnitude, 4 newtons, to the left. So the following are vectors and scalars. You've got displacement, that's a vector, distance, scalar. Velocity vector, speed, scalar. Acceleration vector, force is a vector, weight is a vector, mass is a scalar, momentum is a vector, and energy is a scalar. After that, we did about distance time graphs. So remember that speed equals distance over time. You'll get a list of the equations at the end of this, the ones that you're given and the ones that you need to remember. So the slope of this line on the distance time graph, the gradient, tells you the speed. Okay, so the steeper the gradient, the faster the speed. If the line is horizontal like this, it's stationary. So you can measure the speed of an object by working out the slope of the gradient of a distance time graph. So to figure out the gradient, it's your change in y divided by your change in x. That's your gradient. How much your y has changed, that could have gone up by 10, divided by how much your x has changed, it could have gone across by 2. So 10 divided by 2 would be an example for that. Speed just tells you how far something is going. Velocity tells you the direction it goes as well, because velocity is to do with direction as well as speed. So if an object's accelerating, its velocity is changing. So we call that idea acceleration. Acceleration is change in velocity over time. The letter V is often used to show final velocity, while U is used to show the initial velocity. So sometimes it might be given that as well. So that's distance time graphs. Let's now move on to velocity time graphs. So when it comes to velocity time graphs, okay, you have velocity on one axis and time on the other. Over here we've got a small acceleration, and over here we have a larger acceleration because of that steeper gradient. Over here the velocity is staying the same, so that's a constant speed or a constant velocity. So the gradient of this graph tells you the acceleration. The gradient of this graph tells you the acceleration. The slope of this graph tells you the acceleration. So again, y divided by x, that tells you the acceleration, how steep it is. If you have a velocity time graph like so, and you figure out the area under the graph, so there's two shapes here, the area under the graph, that will tell you the distance travelled. So it's a triangle. If you multiply that time by that velocity and then divided it by 2, that will tell you the distance travelled under part A. And you figure out, if you times this time by this velocity, you figure out the distance travelled there. So I'll tell you the overall distance travelled in A and B if you added those two together. So you've got the method for that over here. So triangle A, add rectangle B, find out the area of triangle A, which is half base times height, the area of rectangle B, so that's base times height. After that we move on to forces. So remember, free body force diagram show all the forces acting on an object. So you've got weight, lift, drag and thrust on a plane. Several forces act on an object. The total force is called a resultant force. So the two forces can be combined to one to have a resultant force. So you've got one going this way, that could be 10 newtons, one going this way, so that's 3 newtons. The resultant of that will be 7 going this way. If objects are stationary, the resultant force is 0, it remains stationary. Okay, if an object is stationary and the resultant force is not 0, it accelerates in the direction of that force. Okay, if the object is already moving and the resultant force is 0, the object keeps going at the same speed. So balanced forces, resultant force of 0, objects carry on at that constant speed, be it 0, be it 10. Okay, but if the forces are unbalanced, if there is a resultant force, the object accelerates, and it accelerates in the direction of the resultant force. Okay, in each of these pictures on the next sheet, so that's just below, the car is moving from left to right. Okay, so to summarize, balanced forces, no resultant force, constant speed; unbalanced forces, resultant force, accelerating. So these are balanced. So sorry, the car below is moving at a constant velocity. Frictional forces mean that it's balanced. This one accelerates to the right. This car is slowing down. This leads to an important equation known as Newton's second law. So everything we've discussed so far is Newton's first. This over here is Newton's second law. So force equals mass times acceleration. Okay. That also leads to another idea, which is weight is equal to mass times gravitational field strength. Okay, remember that Newton's third law states that if Object A applies a force on object B, then object B applies the same size force in the opposite direction of object A. So if you push a wall with 10 newtons, it pushes back on you in the opposite direction with 10 newtons. That's what Newton's third law tells us. Okay, we'll now move on to stopping distances. And the thinking distance is a distance travelled where a driver is reacting to the situation. So in other words, it's to do with the reaction time. So that's to do with the speed of the car. The driver's reaction time has been affected by drink, drugs, alcohol, tiredness, or distractions. And the braking distance is a distance that we actually travelled while the driver is braking. So that's like road conditions, brakes and tyres, the speed of the car, the amount of friction between the road and the tyres. So stopping distance equals thinking distance plus braking distance. That equation is never given to you. Remember that we can measure reaction time of somebody by dropping a ruler and seeing how far up the ruler they can catch it. Right, momentum. Moving objects have momentum, so momentum is equal to mass times velocity. Remember, it's a vector, so has magnitude and direction. And when we are stopping an object, we are changing its momentum. So to do that, we need to apply force. So force is equal to change in momentum divided by time. Okay, this formula can help us to understand the forces involved when objects collide. So or when an object has a large force applied on it. So say you're trying to brake. Okay, this helps you understand that. So if you're going along in a car and you hit the brakes, this is why certain things happen. Okay, remember, if you're hitting the brakes, there's a force applied on you, so you're trying to change the momentum. The larger the force, the quicker that change in momentum is going to happen. So if you're catching a ball, you bring your hands in to increase the time for the change of momentum, so it doesn't hurt your hands so much. Crumple zones do the similar sort of thing in cars. Okay, so they increase the time for the change of momentum to make sure that they don't fall over, to make sure that there's not a large force actually applied on something inside the car. So to summarise these ideas in Newton's laws, remember Newton's first law tells us if there's no forces acting on an object, it carries on going at the same speed. However, if a force is applied, then an object accelerates. Newton's second law tells us the equation for that. Newton's third law is if you apply force on an object, it applies a force back on you, and then it goes on to momentum and the force is applied in momentum. Carrying on momentum, you've got the idea of the conservation of momentum. Conservation of momentum tells us the mass before a collision or an explosion is the same as, so the momentum before a collision or an explosion is equal to the momentum afterwards. They're the same. So here's an example of us actually doing that. We've got an example calculation here where we're calculating the momentum of the van and the momentum of the car, and therefore you can figure out the total momentum beforehand. So you can work this through in your booklet, or you can pause the video and watch it through. And then you know what the momentum is before, so the momentum afterwards is the same due to the conservation of momentum. So therefore the momentum of the car afterwards we know because we've got that 4 and that 400. So you can take that away from the total momentum to figure out the momentum of the van, and then divide that by the mass of the van, which we know as well, which means we can calculate how fast it's going. So typical sort of 6-mark question that you could get on momentum. Moving on quickly to renewable or non-renewable electricity. Remember, you need to know about how electricity is generated. It's a very simple, straightforward process. Remember, non-renewables are coal, oil and gas. So that fossil fuel is then burnt, so that makes chemical energy into heat energy. That heat energy is then stored in that water and steam and transferred into kinetic energy, which turns a turbine as kinetic energy, and that turns a generator as kinetic energy, making electricity. Right. Nuclear power stations also use that process, but there's nuclear fission taking place, which heats the water rather than actually burning the fuel. So you need to know the advantages and disadvantages of each of these. So fossil fuel stations can be located pretty much anywhere, and the fuel source is reliable. Anytime you want energy out of it, you can get it. The problems are that they produce carbon dioxide when they are burned, which contributes to the greenhouse effect and global warming. Also makes sulfur dioxide, which causes acid rain and breathing problems. Nuclear fuels, they're non-renewable. They're going to run out one day, and the accidents are dangerous. Okay, it could be a high cost to actually decommission this, but they don't produce any harmful gases like carbon dioxide and sulfur dioxide. If we think about renewables, these renewables can be replaced one day. Okay, they're not going to run out, and that means that they're conserving fossil fuels. That's great. So there are many different forms, and you need to know how they work, and also the advantages and disadvantages of these two. So biomass is like burning waste from animals, and we've got that idea before, and that heats water, turns turbine, turns a generator, makes electricity. Geothermal, hot rocks on the ground, heats water, turns a turbine, turns a generator, makes electricity. Hydroelectric, okay, is when water falls down, rainwater is collected behind a dam, or water from rivers collected behind a dam, and then that water turns a turbine, turns a generator, makes electricity. Solar panels, light shines down and directly is made into DC electricity. Tides, water moves in and out, and those tidal forces fill up several meters, and they turn a turbine, and that makes electricity. Wave turbines move through the turbine, turning a generator, making electricity. And wind blows directly onto a fan, which turns a turbine, turns a generator, and that makes electricity as well. So they're all pretty straightforward there. All of them, apart from solar panels, involving turning a turbine, which turns a generator, that makes electricity. So you need to know the advantages and disadvantages of all of them. So I've written does not pollute here. What I mean by that is it does not create CO2 or SO2. You need to say that. It does not produce greenhouse gases. However, when you're making these, that does produce greenhouse gases. So all the concrete involved in making any of these structures or transporting these structures does release carbon dioxide to the atmosphere. Okay? All of them are renewable, so they'll all be able to be replaced. All of them end up conserving fossil fuel stocks, which means we don't run out of fossil fuels. Key thing with hydroelectric is it's very reliable. It can be turned on and off very quickly whenever you need it. The disadvantage for each of these: geothermal only works for certain locations. Hydroelectric only works where there are hills, and it also destroys habitats and farmland potentially. Solar panels, expensive to set up, and only work when it's sunny. Tides can disrupt where ships go, can lead to some animals having to leave where they live. Wave turbines can also disrupt where ships go. Again, some animals might need to leave where they live, but it doesn't really produce large amounts of electricity. And wind turbines can be noisy, some people think they're an eyesore, and they can also kill birds if they're not careful. So there's certain issues when you're thinking about the power station you're actually using. You need to think about how much it costs to set up, how long it takes to set up, the running fuels and the costs, how reliable the fuel actually is, the location, and the impact it actually has on the environment. Right, so once we've got this electricity, we need to move it around. That's what this thing over here is. This is a picture of the national grid. So in a national grid, you have a power station, a step-up transformer, power lines, a step-down transformer, and a house. The idea is the power station produces electricity, step-up transformer increases the voltage, that decreases the current in these long power lines. Now these long power lines have high resistance, so if the current is low, they're not going to lose a lot of heat from these power lines, which makes the whole process more efficient. That means that the energy is transferred to the houses in a more useful manner. Okay, there isn't so much waste, and that is how we can make sure that we move electricity from A to B, from one place from the houses, from power stations to houses, usefully without wasting a lot of energy in the long power lines. So step-up transformer increases the voltage, decreases the current to minimise heat loss in high resistance wires. Right, so just to talk about those equations, these are the equations you have to remember. Speed equals distance over time, distance equals average speed times time, acceleration equals change in velocity divided by time, weight equals mass times gravitational field strength, momentum equals mass times velocity, stopping distance equals thinking distance plus braking distance, efficiency is the useful energy transferred by a device divided by the total energy supplied to the device, and the other equations that you'll be given are the final velocity squared equals the initial velocity squared, minus initial velocity squared equals 2 times acceleration times distance, and force equals change in momentum over time. So you'll be given those two equations on the front of your test. And the only things I want to add to this is you might want to look up the 9 forms of energy and use each of those, because they do offer. It's just one of those things that's consistent that you need to know. So make sure that on the Bite Size website or somewhere else you look at the 9 forms of energy, and that you know them and you can apply them to situations. So to quickly write through them, you've got chemical for food, you've got kinetic for moving objects, nuclear for when you're splitting atoms, sound, obvious, light, that's obvious as well. Then you've got electrical for electrical devices, and you've got elastic potential, gravitational potential as well. So you've got all these different forms of energy. Make sure you know uses of them and where you'd find them. Okay. Thank you very much. That's the end of the Physics CP4 video. All 3 videos will now be posted online. Please make sure you revise for your CP4 test, and good luck.